All right, we're good to go. Shreya, please take over.
Okay. Hello and good afternoon, everyone. This is Shreya Pohekar, and I am Null Bhopal chapter lead. And today I'll be the host for this event. So, if you don't know what is Null in general, let me brief a bit about it. It's an open community for security. It's a place where like-minded people come together and share their thoughts and have discussions regarding things on security. So we welcome both the genders, male as well as female, and yes, it's free to attend for all. Um, who are we? We are India's active open security community, and now we are extending even abroad in chapters like Amsterdam and Dubai, and we have currently 15 chapters that are active and running. So null community is basically the combination, or it contains people from different domains, like they are penetration testers, they are either security managers, security admins, security ninja, and any other field or thing that you can think of. So what do we do? That's basically eat, sleep, drink, and security. There you can add anything you want, but yeah, security should be the point. So there are basically four concepts that we have in under Null. So we have the monthly meets. In monthly meets, we have speakers who take up sessions that run mostly for an hour. So the sessions basically give the overview introduction to the various topics that are in security. Then we have the Hamla session, that is a full-on hands-on workshop where people attack on different labs. So that is basically the offensive security. Then we have the Null Bachao, that's the opposite of the Hamla. That is, we create defense. Means we do sessions or workshops that are fully focused on how to defend our systems. Then we have the Pulya session. So Pulya session is basically the workshop, we can say, that is like conducted in order to bridge the skill gap between the members of the community, because the community has like all sorts of people from students to professional. So to say that we are on the same page means like everyone is on the same page and everyone understands everything. We conduct sessions like Pulya session. So yeah, there's also a conference called NullCon that takes place every year in Goa. So that's basically a conference. It has nothing to do with Null, but just information you can have. And then there are discussions on mailing list, means any doubt you have, you can like ping or you can message over this mailing list and someone will be there to help you out on your issues. Then what's in for you? So, okay, you get a hell lot of learning because you are between the people who are like sharing your feel, or you are who are like uh, present in those fields and learning into those fields. So that's one point. Then the second is exposure to security industry. As most of the people are involved with Null, so you get exposure in your college days, even like I got in my college days. And then obviously when you are within the community, you get to increase your network. Like for Null Bhopal, you connect with Null Bhopal, but also you get to connect with peoples of different chapter like Bombay, Bangalore, Delhi. So yeah, you increase your network and you get your name out there. And you get out your name there by taking sessions so that people get to recognize you that this person somewhere he or she took the session for this. So yeah, you get your name. And then how you can be a part of Null. So you can just go to null.co.in and register there. You can join the mailing list, you can attend the meetups, and you can take the speaker sessions. So that was about the Null. Today we are having our Null workshop that is taken by our speaker, Mr. Chirag Jariwala, and he is an IoT security researcher at Secure Layer 7. And today he'll be presenting upon reverse engineering with ARM. So all the very best, Chirag, and now you can take over.
Hello everyone. So yeah, today's session we will see how you can get into the ARM. ARM is the future of CPU architectures because, as you know, the recent announcement about MacBook Pros, which is coming out, which will be in ARM. Likewise, many devices in the future will run on ARM. So yeah, and IoT devices generally all of them runs on the ARM architecture. So the today we will see the 32-bit variant, which is like up to ARM7. There are various version of ARM. So there is starts from ARM 5, 6, 7 up to 7 it's 32-bit. After 7 it's basically 64-bit. So yeah, ARM 8 and 9 and 11, 10 and 11, so this will be like up to your 64-bit. Even your phone, it runs on the ARM. And likewise, even sometimes Wi-Fi routers as well run on the ARM. So bit of the introduction about me, who I am. So my name is Chirag Jariwala. I'm from Secure Layer 7. So I do IoT security research over there. Like I work on IoT security related projects. And yeah, I'm OHCP certified as well. Like, yeah. And I also write various kind of blogs which are related to IoT security, cybersecurity, and online privacy. You can check that out at cjhackers.net. So you will see various kind of articles related to IoT security and cybersecurity in general. I write on a monthly basis. So yeah, you will have the question why one should learn reverse engineering. So let me brief about this, why you should learn reverse engineering and master this skill. A complex program or a system casts many shadows. One of this is your development environment, and everything else is a weird machine whose instructions are actually combination of your well-designed features, but it will run the attacker code. So what I mean is, like, when we talk about any complex system or a software, more the free features you bring inside of it, the more vulnerabilities will be there. It's a universal truth when it comes to cybersecurity in general. It applies to embedded environment as well. So in the embedded environment, most of the time your software is highly customized and very specific to that particular hardware. For example, router will run a specific set of software that CCTV camera won't. Or let's say your Android smartphone is running basically your Java engine and all kind of stuff that might other IoT devices might not run. So like, yeah, so that's, you can say, reverse engineering. With the help of reverse engineering, you can learn how the software behaves at a low level, or at a very low level, at the binary level, or you can say at the assembly level. So that way you have a deeper understanding of the software and you will be able to exploit and find out the zero-day vulnerabilities in such a critical systems and the environments where the software is highly customized to that particular device. Yeah, so this code is from Sergey Bartos from TroopersCon 2010. So this was the university professor. You can Google search about him. He has a quite good research on about memory corruption and everything. It's a really nice talk. You just Google, search this name on the YouTube. Very fast talk will be there about how the memory corruption flaws and like why these are important. So yeah, as I said, more functionality equals to more wider attack surface, more custom codes equals to more possibility of 0 days. So this is another reason you should learn ARM reverse engineering is because these are the two main branches in IoT reverse engineering. One at the firmware level and one is typical malware analysis. So you can say it's kind of a red team and a blue team scenario in IoT security. So if you have a reverse engineering skill, you can go in any one of this sub domain of IoT security. And like apart from ARM, there are other architectures as well. MIPS is the common one, and RISC-V, which is new. So RISC-V is pretty much open source entirely. Like I can give you one example. The recent, if you have heard the news, the folks from the IIT Madras folks, India invented their own CPU, and it was on the RISC-V. So why they picked up the RISC-V architecture? Because it was the completely open source. But as of now, there is no fully stable operating system available to this architecture. So it's better to stick to ARM and MIPS architecture. But ideology and the instruction sets behind the RISC-V is the same as MIPS and ARM. So if you learn any one of them, you practically are learning other two parallelly. You concepts will be almost same, 90%. So after that, you have two subfields, two sub branches which divides like exploitation and the threat research. In the threat research, you do like botnet behavior analysis. Like let's say you have a Mirai botnet attacking your critical system. So how you will defend again and how you will configure your firewalls, how you will reverse engineer that malware and see its behavior, what kind of traffic it's sending to the C2 server, likewise. And the backdoor hunting. Oftentimes, there has been cases like critical system gets backdoor, even if it is air gap. Now these days, there are a lot of ways to even hack the air gap devices on physical through the physical access. So once it's happened at the most of the time supply chain. So these are backdoor hunting pretty much applies to supply chain. So whenever you're like, let's say you purchase a router from a third party vendor and you are not sure about the origin of that router. Let's say you purchase from a malicious person. He put a backdoor firmware inside the router, like, and your basically where you install your company gets compromised. So how you will identify that backdoor? So yeah, that is also can be done with the help of reverse engineering. And yeah, typical exploitation stuff can be also done with the reverse engineering, which is a stack overflow, heap overflow, and other exploitation techniques you can apply. So like from reverse engineering, the same concepts you can apply to exploit development after for identifying this kind of vulnerabilities, whether the it has this kind of vulnerabilities or not. So you may ask why one should learn this. Another thing is like, yeah, these are the some pictures from the like If you search some showdown queries, you will be like get thousands of routers infected with malware, or there are actively tons and tons of botnets are scanning internet. So if you go on the gray noise, you can put a query to search for a Mirai botnets or a telnet scanners. So there are lots of malware out there who scans for the IoT devices for the default password. So basically, IoT security is still pretty much lags far behind when it comes to even basic security implementation. And like we have these things like default passwords and all kind of stuff, because people are not aware how to handle this all stuff in IoT security, because IoT itself as a field is a very new. It has been like they're like booming since like past 2 3 years. And yeah, security, IoT security is it's a really niche area of work. Who does it, you may ask? Who does this all kind of, you know, pain, headache kind of tasks? So yeah, the one of them is CIA. So if you go to WikiLeaks, they have pretty much reverse engineer like well-known routers and found out the 0 days and actively exploiting them. So, and other guys are like me, white hat security researcher who like to publish cool talks about the devices they hack, and publish the research at the various security conferences. And the nation state actors as like, yeah, some the well-known example for this will be Stuxnet, right? So Stuxnet was pretty much a nation state attack on uh, the country of Iran, and Iran nuclear power plant. So it was believed to be done by in cooperation with United States and the Israel. So that was it falls under the same scenario. You are end of the day hacking the OT environment, which has a critical systems. So you may ask, what will be the knowledge requirements to learn reverse engineering? So this is the knowledge checklist. First will be Linux basics, because yeah, more than 90% of the IoT devices run Linux. There is no alternative at all, and no one is crazy enough to run Windows 10 IoT code on the Raspberry Pi. That is like 0.1% of the people who run Windows and other operating system in the IoT environment. Most of the time, it will be some custom OS, custom kernel compiled, and even times they have their own linkers. From my experience, I know this is especially with it's a case of Cisco routers. They use their own C libraries, and they pretty much takes everything from a low level and the memory handling for a security purpose very seriously. So it's really hard to compromise Cisco routers just because of that. And like yeah, sometimes you have custom drivers as well. So some routers have the file storing capabilities over a USB. You can plug a USB flash drive behind the router and share that file. So that even USB requires basic drivers or a kernel modules to operate. So that is made by oftentimes third party software developers. How program works in Linux. So you need to know how the execution flow is there, like what is the structure of executable binary and etc. And yeah, pretty much basic understanding of assembly. So we will see the these two today. And the first one is pretty much, yeah, if you are in the regular pen testing environment, you should know Linux basics. It's most important. What things we will see today? So as a topic, we will see the Linux internals, ELF format, Syscalls, kernel modules, how this all stuff works. ARM assembly basics, we will see ARM instruction sets. We will compare them existing 32-bit or x86. It's pretty similar. So if you know 32-bit already, your like 60% of the today's session is already covered. So if you know already x86 architecture, it's pretty much same, not 100% same, but yeah, if you know assembly, you will be having really easy time to understand ARM as well. ARM reverse engineering lab setup. So there are lots of ways to do that. One is user space emulation with Q emulator static, full blown emulation with ARM Word CPU. So for that virtual machine, you will be link is provided for that, and the Q emulator NAT network setup. So we will basically set up a network for our virtual machine, and we will be able to have full network capabilities for that virtual machine, so we can do various tasks such as SSH into it, or like, let's say you wanna in the future you wanna ch root inside some ARM firmware and expose the network services, so it will be easy. So we will see also GDB, GNU debugger, and Radar A2, memory corruption flaws. So today for demo purposes, we will see the basic buffer overflow one, uh, and custom shell coding, like how you can make your own shell code. And this is not definitely, we are not gonna see this, that how to explore the universal power supply like Mr. Robot does in season 2. So that's, we are not gonna do that today, obviously. So I hope you guys know this picture. So this picture is basically the well-known woman scientist from the NASA. She made assembly code. So the paper she is showing off, it's an entire assembly code which made possible the entire lunar landing mission. So yeah, the assembly made it to the space years back as well, and made us to reach the moon. So yeah, Linux. So basically, what I'm relate this picture with is Linux has this philosophy. In Linux, everything is treated as a file. So like basically from even like doing basic tasks such as opening port. So whenever you open a port, there will be a special kind of file created for that port, and the data will be exchanged from there. So this is ELF structure we are seeing over here. So yeah, the basic ELF structure contains this following sections. So ELF is nothing but your, in the Windows terminology, it's .exe kind of file. In Linux, we call it ELF. So it will have the this kind of sections. .txt contains your assembly instructions. RO data has uninitialized stuff, and data is basically where your global variables and everything are stored. And there will be a section header table. So for each section, there will be a header which denotes the what kind of section it's basically starting. So this is typical screenshot taken from your binary. So whenever you see the sections inside the binary. This many of them will be there. Like GOT is your global offset table. BSS is for uninitialized data. PLT is a procedure linkage table. .txt, as I said, it stores your instructions. And the stuff will be there, like it may tell you the GNU version, which compiler version compiled it, and often time you will also have this function name symbol table will be also there, like it will denote the what are the function names and everything. So let's see ELF header structure. So whenever we see the ELF file, how the header structure is defined. So let's see the first command, then you will understand the use of this. So you will be provided the .tar.gz file. So basically that .tar.gz file you have to extract it. You can do that with this command. Yeah. So once you extract it, you will get this folder Null Bhopal workshop. You can change it inside of it. And there are binaries given over there. So yeah, a bunch of binaries are given to you. So these are for our little experiments, you can say. So let's see. So to see the header of any binary, there is a Linux command called read elf -h. H stands for header, hello world. So yeah, it contains this kind of information. So you must be wondering where this all information is coming from, where the read elf command knows that it is elf64 and is a shared object file, not a static one, and it's a little Indian one. So that is the specific structure for that. So it follows at the operating system level. This is the pseudocode, and these are the types of you know metadata it contains. So yeah, there will be like a different stuff. So e underscore ident is a 4 bytes. So in Linux, any file, first 4 bytes are magic bytes. Then we have e underscore ident ei class. Ei class will have 2 bits, 0, 1 and 0, 2. It's only 1 byte long, so it will denote 32-bit and 64. If it is 0, 1, it means 32-bit. If it is 0, 2, it's a 64-bit. And we have a little endian, big endian as well, and the ELF type and ELF architecture. So these are the values of EType. So EType, what was the EType? If we go back, EType is your nothing but it tells you what kind of file it is, whether it's a dynamic or it's a statically compiled or whatever. And E-machine tells you the architecture. So what kind of architecture that is present. So let's compare the headsdump output for both ARM and the 64-bit one. So you can do this with headsdump-vc, and you can just cut the rest of the output with the head command. Now, as I said, the first 4 byte 1, 2, 3, 4 is your basically it's magic bytes, right? So yeah, it's there. It says ELF. Second is this one. So it says for me it says 03. This 0300. And so what is 0300? If we go back, it's a dynamic, right? And yes, it is
Chirag,
dynamic.
Chirag, I think your
DYN.
screen is stuck.
Type is DYN. So EType, we got 03, so it was dynamic. And if we check for the static one, it says executable. And executable, if we see over here, exec should be 02. And it's 02, right? So first, this are for this 4 bytes denotes our architecture, and this one denotes our what kind of file it is, executable or like dynamically loaded. We will see the difference in the moment, like what is the dynamic and the static ones. And e-machine will tell like what architecture it is, like it's 64 or like 32-bit. So 3E00 is for 64-bit. 3E00 it's for 64-bit, and for 32 should be this one. So if we again check the table, yes, 03 is x86, which is nothing but your 32-bit. And if we check for the ARM, okay, I will we will see this one later, but yeah, it will show this as per the slides I have put the image. Yeah. So ARM will be this one, which is your 28, and yes, it is 2800. So now you understand like where it's getting the all kind of this metadata. So as I said there will be a header section at the start, and there will be other sections, and each of that section will have their own respective header section. So your binary contains all of this metadata that your operating system is able to parse it and know what kind of binary it's gonna execute and what to do. So yeah, these are the particular sections when it comes to the any Linux binary. The first one is .txt, the where program execution instructions are stored, and those are architecture specific, and which is understood by the target CPU. So let's say if you have a Broadcom CPU, it will only understand ARM because it is manufactured to run ARM operating system and everything. And if you talk about Intel or AMD, those guys are, as we know, are usually x86. The data section contains stack, heap, and local and global variable storage. PLT contains process linkage table, which calls your external libraries and the functions to be loaded by the dynamic loader. So yeah, the dynamic loader ld.so, it's basically look for your function addresses in the library, external libraries, and load them into GOT, global offset table. And the global offset table, it holds addresses of the function to be called during program execution. So you may ask why one should know about these all sections. The one example, best example I can give is about GOT. So when you are doing this is the technique, exploitation technique on return to libc or a raw gadgets. For that, one has to look at the global offset table to get the specific function addresses to craft the you know gadgets, drop gadgets. So yeah, uh, the one, let's say the difference between the dynamically loaded library and the static one, how they look like under disassembly. So if you see over here, this is the dynamic one, and if you load it inside the GDB, it will tell like put as PLT. So it looks the function address from the dynamic link loader ld.so from PLT, procedure linkage table. Well, it's clearly mentioned in the GDB put as PLT. And whereas in the static binary, it will, so this is the command read elf relocks. So this will show all the reallocations which happens in the dynamic one. So it will tell you what are the addresses it's gonna look in with the help of dynamic link loader. So as you can clearly see in the dynamic one, it looks for the putters, but in the static one, it doesn't have any reallocations. You can verify this again with our given binaries. Read elf relocks, and then let's say so read elf relocks for the dynamic binary. It tells you all the reallocations it's gonna look for. So yeah, it's a hello world program, so it typically looks for the as usual printf. But if we check for a static one, oh, oh, I guess some functions in the x86 are different. But for the ARM, it's pretty clear, like it doesn't look anything. And yeah, also in the GDB, you will have it will directly say put as, not put as PLT. That will be a difference. There is one more way to identify this is with help of strace. In the strace, it's a signal trace. It's a Linux utility to see the system calls executed by any binary. So we will see about the syscall in a brief moment. So strace command basically see all the syscalls by the executing program. So first you will over here say is mmap2, memory map 2 is happening. And what this memory map is doing is trying to access the dynamic link loader ld.so preload. And in case of static binary, it directly does the syscall to the right. So why it directly did the write syscall, because yeah, any whenever you want to write to a shell, or as I said, write to your screen, according to Linux specification, everything is treated as a file. Even your terminal output is considered as a file. You have to write to it, and to writing anything to a terminal window, your file descriptor is 1, and the rest of the data, which is hello ARM, and the size, which is like 10 characters. So this is the write syscall. So it's not happening here because yeah, that function is getting loaded by the dynamic link loader ld.so, but it's happening over here directly, and we get the write syscall just because we compiled it statically. The download links are provided. So one more last terminology, and we have to understand is this one, which is your ABI. ABI is nothing but application binary interface. Application binary interface is typically, if I talk about in the web technologies perspective, it's like a API. But for what? It's for your operating system. So basically, who implements this ABIs? It's implemented your operating system's kernel. Kernel provide these functions. So normal user space programs can execute highly privileged tasks, such as let's say opening a network socket or anything. So that all things and privileges are handled by your syscall. So basically, you have a two separation in the usual Linux system. One is user space and one is kernel space. In the kernel space, in the ARM, it's only 3 levels. The x86, the normal architecture has a more than 3. In the ARM, it's like there will be a supervisor. There will be a kernel isolation between user space and the normal, kernel programs or a kernel modules or a device drivers. And yeah, supervisor is a like a program which handles the everything. It handles the data going through from the syscall between user space and the kernel space, and it takes care of the security as well. Syscalls implement ABI. So yeah, the syscall is like you are actually calling those ABI functions and allow user space programs to have execution access to certain kernel functions. First, very most important, we will see is Syscall Open. So Syscall Open is for opening a file inside Linux environment. Returns the file descriptor for a given path for any file. So if you use this function and if you give the path, and there will be a certain flags you can assign, such as o underscore read, it opens the file in the read mode. O underscore append, it opens a file in append mode. O underscore create, kernel creates a file in the file which for a file name doesn't exist. And this is like a special kind of flag which is used by pipes and sockets and the terminals. So files which are not a regular files but a special kind of files. Since again I am repeating, everything in the Linux is file. Syscall read. So yeah, as if the name suggests, read means you read the data from the specific file descriptor which you obtain from the open syscall. So each call reads up to some length number of bytes into memory pointed by the buffer from the current file offset of the file referenced by the FD. And yeah, that file descriptor you get from Open Syscall. On the success of the number of bytes written into buffer is returns. On the error, it returns -1 and says the error number. Like yeah, it will if there is any error reading from a file, let's say due to permission issue, you are like normal user and trying to read some data from the root, the reads is called, then will return a value of -1. And yeah, many more stuff it can do. And the final one is write. So write is again used along with open syscall. Once you open the file, you can not just read, but you can write as well. So by using a file descriptor obtained from the open syscall, you can pass it to the write syscall and pass a certain amount of data from your memory. So this is nothing, buffer is nothing, you're like, let's say data from your memory. So I'm trying to point that into the memory. And the size underscore is t is nothing but how long your data size is, like how many bytes you're gonna write to that particular file descriptor. So to know about syscalls, you can use this command on any system, which is man syscall, and it will tell you about syscalls which are available according to your latest kernel version. You can see all the various kind of syscalls. Yeah, there will be right, yeah, over here, and from which kernel version it started providing support and every kind of stuff. There is a command called ManMan. So you can also get manual for a manual. So ManMan basically tells you like what kind of manual it can provide you. If you want to see the particular system call, you can do it with man2. So man2, and then let's say write. It will show us the write syscall manual about the write syscall. Because what happens is if you don't use this, you see, it's not a syscall, it's a C program library function. It's like a it's a, this one is for a command. Yeah, see the difference, it's different. If you don't use the man2, man2 specifically says the type of the 2 is for the, like that number represents the type of manual. And when looking for the manuals for the syscall, you always use the, yeah, man2, and then otherwise it will show the manual for the commands. And yeah, you will be scratching your head for an entire day. Yeah, you can search like this man2 and like the name of the syscall, let's say socket. So this socket can be useful for, you know, making connections and everything. So this example we will come back for. First we will see the basics of ARM assembly. We will visit this. So we will see the some overview about kernel modules. So why looking at the kernel modules is also you should do it, and why it's important. So yeah, kernel modules are pieces of small code. It's like a Lego puzzle. So your kernel is like pieces together with many other drivers and everything to provide support for various kind of hardwares out there. The core kernel cannot support everything, so it has this more support for a introducing modularized code while it's running. So that is we call as a kernel module or basically device drivers. So kernel modules extend the functionality of the kernel without need of the reboot the system. So that's why it's not like a Windows system with each update you have to reboot. That's why in the Linux, whenever you update your system, you never have to basically reboot, because whenever a new driver update comes up, everything is loaded as a kernel module on the fly, and kernel starts the execution automatically without doing the reboot. That's the now you understand why Windows update are usually you need to reboot and why in the Linux you don't. When Linux boots up, many networking related hardware such as your Ethernet, Wi-Fi, Bluetooth, everything is as a loaded for this have a software, their own software. Every chipset have their own software, and that software is nothing but a kernel module. So how you can find the various kernel modules? You can find it under this path, lib modules kernel underscore version. So yeah, kernel underscore version is nothing but basically if we talk about this, it will be your kernel version. This is my kernel version. I'm using latest one 5.6. And it will show as a .ko file. So ko file is nothing but your kernel object files. So you can get the information about any kernel module with mod info command. So yeah, mod info will tell you the information about that kernel module, like what it does, like its generic Bluetooth USB driver, and like what is its type, like it's ELF32, so it's a 32-bit, and like its architecture is ARM. This is the basic C program for a kernel module. It's a very basic hello world. So yeah, the usually the metadata is set by this function macros over here, module underscore license. So that tells like what kind of license you want to use. There will be author underscore description. So there will be like lot of function macros provided by your kernel.h, and you can set various kind of metadata. And like yeah, to all whenever you load the kernel module, it always look for this underscore init, and it's always type of integer, because yeah, always it should return some kind of value. Otherwise if you don't return it, it won't load it. And yeah, there is a underscore exit as well, so which cleans up your module, so it will perform the task. You can like a print k is for a printing to the basically your d message. So we'll see the example. Yeah, in this screenshot you can see I created my own custom kernel module. I compiled it, and with the mod info command, once it's compiled, you can see the information that I provided in my source code, which was like the license and the author name and the description, which is the same as what we can see over here. And yeah, you can insert any kernel module with the insmod command, which is, and then file name, the kernel object file name. And yeah, so what this module was doing when we initialized it, we were just printing this message with a print k. print case for print kernel, and this is the flags, like what type of message is there. So it's a informational kind of. You can like print alerts and many types of others are available there. So as you can see, when we load it with hints mod, it says hello IoT as it should do. And upon the cleanup, it does cleanup on module. So why we just saw this concept? Because yeah, in IoT devices, oftentimes the kernel module attacks are discovered. This is the Cisco Talos report on the Netgear router, which has a USB file sharing feature, and then they find unauthenticated remote kernel arbitrary memory read vulnerability. So they were literally able to read the memory remotely by just plugging in the USB. So it was the vulnerability in the kernel module itself. So yeah, enough of the theories. Now you must be, you know, show me the, demo kind of mood right now, because we saw a lot of Linux demo and all kind of basics of Linux and everything at the low level perspective, which was necessary for our understanding and how things function. And this knowledge will help you a lot when you come into the reverse engineering, and you know you won't have basically like stuck in the doubts that how to proceed and what to do and where to look for the stuff. So for that overview perspective, the entire that low level theory for the Linux was provided to you. Now we move to the main part of this workshop, which is ARM assembly basics. So there are two types, little endian system and the big endian system. So in assembly, when we say little endian, so you will be storing least significant bit to the lower memory address, and high at high memory address you will be storing most significant bit. And in the big endian, it's completely opposite. So this is the difference between ARM and x86. So in ARM, there is R0 to R5, and in x86, the prospective ones will be like EAX, EBX, ECX, EDX, ESI, and EDI. So these are your general purpose registers. In R R6 to R10, those are again general purpose. You got extra more registers for a general purpose. Specifically, R7 holds your syscall number. So yeah, we just saw what are the syscalls you can use, like to create a file, read from a file, and do the operating system related tasks with the help of the kernel functionalities provided by the syscalls. So those syscalls will be called by the R7 register. R11 is nothing but a frame pointer, which in x86 correlates to EBP. And below are the special purpose registers. R11 is for intra procedure call. R13 is for a stack pointer, ESP. R14 is your link register, LR, and the PC program counter. And like our usually if flags, in this one we have CSPR, current program status register. So it will carry our flags, like when you have, like, let's say you have a addition, or like you have extra carry flag, that all will be added to the CSPR registers. So you must be asking how to see the syscall numbers. Like you wanna call a certain syscall with the help of R7 register. So how you will get that syscall number? For that, it's basically, yeah, it's a this command you can see in this part. USR include ARM Linux GNU EA BIHF and ASM. We will see this improvement with the help of our virtual machine, and we will see this basic hello world ARM assembly program as well, like how you can use the write syscall and put a message on the shell. So if you wanna know all the instructions sets, this is the link. So this is a cheat sheet kind of link made by the ARM folks itself. Let me open this. Oh, it seems like they removed it, but I still have it. I will upload it and share the link again for this PDF. So actually, it has the all instruction sets over there. So these are the basic instruction sets are there. LDR for load from a register, STR to store address of the register, BL is for branch link, compare, CMP is for compare data between two registers, push is to push data from register from a stack, and pop get the value from stack to register, and others are addition, subtraction, multiplication, and etc. So this is the example of load and store. So for first is like in the, as I told, if we saw in the sections slides, that we know our variable goes to the data section. So in the data section, we are defining a variable with a full size word. Word is nothing but the full 32-bit. Half word will be your 64, and likewise. So what is your 32-bit value? So we are saying like create a 32-bit variable with this value. So I'm creating two variables, 24 and 14. Then what I'm doing is in the text section, I creating a function called global function called start. So this will goes to the GOT global offset table. So obviously it doesn't need to check with the help of dynamic link loader, since it's all function address is already there for the execution in the we are pushing it to global offset table. So yeah, start, we will, it's a label for our function. We will say LDR R0 ADR underscore 1. So ADR, this again is getting from this instruction sets. So you can likewise define a label and a reference. These are like a pointers basically. This is nothing but a pointer. So it's like a pointer to the variable one. So ADR underscore where one is a basically according to C program, it will be like star where one. So this is the pointer to the variable one, for which it will get the address, so it value, and yeah, from it's getting the value into R0. Load the address of variable 2 into R1. Load the value of variable 1 into R2. So we are just exchanging the values in between. And store variable value of variable 1 into R1. So it will be basically end of the day, what will happen is variable 1 will become equals to variable 2, and it will be end of the day 24. So this is the memory structure we just saw. So how the stack and heap functions, that's the definition of this. So your stack grows higher memory to lower one. It stack basically decreases. Basically, whenever I say we are expanding the stack, what we are doing is subtracting from the memory addresses to expand it, because the stack is located at a higher memory address. Just after the kernel space, your stack is located, and heap sits on the lower memory address. So inside the stack, there will be this thing called stack frame. For each of the function that they have this own isolated stack, we call it a stack frame. So all of these functions utilize their own perspective stack frame, and which is utilized with the help of these two registers, fp, which is a frame pointer, which denotes the start of the stack frame. Lr is for your, it's a return address of the function. It stores the return address of the function, basically. So yeah, difference between stack and heap. Stack is very fast, don't have explicitly deallocate variables. Space is managed efficiently by the CPU, and memory will not become fragmented. Local variables only are allowed. Limited on the stack size is OS dependent. For 30, obviously 64-bit stack will be bigger than the 32-bit one. And yeah, variables cannot be resized on the fly. You cannot do that if you're using stack. But yeah, heap heap can do, variable can access can be globally. No limit on the memory size. It's a slower, no guaranteed efficient use of the space. There are certain algorithms for heap management, but yeah, still those cannot, as terms of speed, they those cannot still compete with the stack. Due to stack is very simple. It's a stack is like let's LIFO. So what is heap, you may ask? It's nothing but a contiguous region of memory that compose pieces of chunks. It's just like a stack frame. In heap, it has a smallest memory unit called a chunks. And yeah, this all chunks management, linking and unlinking of chunks is handled by the various algorithms. So one of them, so when malloc is the again the syscall. So malloc, when the malloc is called, it returns the pointer to the chunk with the suitable size. So there are these algorithms over there, like this will be like glibc. Glibc pretty much used in the Linux, ptmalloc, jmalloc, tcmalloc. So these are used by the Firefox, Chrome, and magazine malloc. It's used by iOS and OS X environment. These are the like there in the when we define a chunk, there will be a heap pointers in the data structures. There will be like end of the data since end of the start brk and everything. So this is like yeah, how the it initialize the heap. This will be the syscalls, brk, sbrk, map, and memory mapping for everything. So yeah, for this, oops, sorry. So that was the basic idea about the heap. So let's see the other examples. So first, let's come to our setup. Uh, if you guys want a break, there is a no issue. If you are feeling really overwhelmed, like we are just was seeing the theories, we can take a break of 5 minutes if you guys want. So yeah, we take the 5 minute break, and we will come back to our ARM, virtual machine setup. So we are pretty much done with the theories. Let's take a 5 minute break and come back.
So we'll be again starting in a minute. So Chirag will take over.
So yeah, let's get back to our main part of this. So that will be our lab setup, ARM lab setup. So yeah, I have already done the installation of GDB. You don't need to install inside your virtual machine. So you will be just ready to go. So yes, first extract the tar.gz file which was provided to you. You will see this folder, and inside of this you will see other directories. One is ARMVM binaries, some of the binaries, some reversing stuff, and assembly related. So yeah, change your directory to ARMVM. So you will see one directory called network scripts. So for this running virtual machine, you will need the Q emulator. So I have provided the instruction to install Q emulator on the Debian based systems. You can just open the readme.txt file and run the following command. It will install everything what you need to run your Q emulator. So you can run this on your Kali. I'm not gonna run this command because I'm not using Kali. I'm on Arch Linux. So for me, it's a completely different set of commands. But yeah, this one should work for any Debian OS such as Kali Linux, Ubuntu, or the Debian itself. Then this step is the same for any Linux operating system. You just copy the files from the network underscore scripts directory. So this directory contains our two scripts. So Q emulator interface up and down. So this will create our NAT network bridge interface from which we will be providing the everything IP addresses to our virtual machine.
Hey Chirag,
Yes.
actually there was some noise from your side, so if you can do
Hello.
something. Yes, I'm audible.
Your voice is. Wait a minute.
Hello.
Hello. Yeah.
Yeah, that there was some noise from your side, so if you can do something about it, would be good. Like banging noise sound.
Yeah. Hold on a second. Yeah. Actually, it should stop. Yeah. So we will continue.
Fine.
So these are the two scripts over here, which is cumulator IF up and down. So this will do executed when you start and stop your virtual machine. So it will do the NAT network setup for us. So you have to move this inside your etc folder at in your file system. So you will be able to see those pretty much Q emulator. Yep, this too. So that goes inside your etc folder in your host machine, or let's say if you are using Kali Linux, inside your Kali Linux. So once you move these two files inside etc, you are pretty much ready to go after installing your emulator. Go back, and I have provided this script bootvm.sh. you can just run it. Oh, and don't forget to run it with root user sudo. Once you start the virtual machine, you will have this window from QEmulator, and you switch to the serial, and you should be able to see boot is starting. So yeah, once you boot up the system, it will ask you for the password. So password is null, username is null, password is null. And it should give us back the prompt. So we will SSH into this machine so we can have a nice terminal output which we can control. So if your network setup was successful, it should give you IP address. Oops, IP, can do IP ADDR. So IP address would be probably like 168.53 point something. So for me, it's 37. So you can SSH. Yep. Enter the password, which is null, and you should get the yeah, shell. And if you see, it's a ARM right now. Yeah, ARM v7. So yeah, this is our virtual machine ARM, fully emulated operating system, which we can do anything with it. So yeah, first one is to writing our own assembly code. So so that what we are installing, we are installing QEmulator in this set of all packages which I given into the installation command. This is this is the user space emulation. So this one is a fully emulated virtual machine. If you don't want to run a fully emulated machine, what you can do is you can do user space emulation. So for that, you can just simply run this command. Let me walk to the new window. Yep. Some reversing. Oh yeah, it's ARM is there. So this one is ARM. You can run it directly in the QEmulator and then yeah, this is the cross compilation. You can install this as well. This is called ARM Linux GNU EABIHF. So if you do that, you will have a cross compiler. You can cross compile ARM binaries on your main system without any emulation if you like to do so. And then you can just Oh, it's a hello. Okay, okay. Yep. See, it runs even if we are using, you know, our 64-bit machine. We are able to run ARM binary with the help of this Q emulator hyphen ARM. So Q emulator hyphen ARM is for user space emulation. It's a not a fully emulated virtual machine. It can just run specific set of programs. And Q emulator hyphen system is an entirely emulated environment. You have emulated CPU, other components and devices are emulated. Yep, it's and we ran it on our 64-bit machine. So let's start with assembly. So if you open the ASM folder, yep, here, go back. There will be folder called ASM. There are certain files over here. First one is a make file. So make file, what it does, make file basically contains the compilation commands. So when you run a make command, it will actually look for the make file. And what my make file contains. So I'm doing is what my make file is doing is the target is this. It wants to compile a ARN ASM binary. So how it will compile with help of this object file. So this object file where it will be situated, where it will be obtained, it's from this again second target, which is creation of object file. And how this object file will be created it with dot assembly dot s file. So you can assemble it with this command as, and then it will take the file as input and output the object file, and that object file will be used over here and it will be used to output the actual binary. And yeah, when we do make clear, it will remove all our files which were created. So it will just do the file cleanup. So let's put some basic assembly code inside .s file. So let's create these files on our emulated environment. So yes, we have our files. Now let's see the very first one, which was using write syscall. Let's print a simple message to our terminal screen. I'm just looking for my slide. Yep. No. This one. Yep. So this was the program. So yeah, it was. We start with dot text and the dot global. So yeah, let's start doing coding. Dot text dot global, and then we put our the function name, or you can say label, function label, which is start. So this is the default label. From start it knows, it starts the executing our code. Not this one, yeah. So again, so first one is moving syscall number. So syscall number is 4 when we do 32-bit one. You can check the syscall numbers in this file unistd-common.h. So let's check that out first before we continue any further. So it's a USR include. Okay, this one, first folder. So yeah, and cdasm cat unistd.h. To move somewhere else. Let's see. Okay, I guess the file name is also changed over here. Oh, it's a unistd common.h. My apologies. Yep. And you can just search it with grep. The first to write to the screen, we need syscall number for a write, which is 4. So 4 is for our syscall number, which we will push to the R7 register. As we saw previously, R7 takes syscall number. So let's do it. So let's go start. Then we will just use move to which register, which is our destination register R7, and we will push 4. So we move R7 to 4. So now, as I told here, the R0 and R5 are useful for the function arguments. So our write syscall takes a function arguments. So what are those arguments? Again, you can check that out in your manual, Linux manual. So let's see. Man2 write. So it takes, these are the function arguments. How much are there? 1, 2, and 3. So basically R0, R1, and R2 will be used for this function arguments. And we already know the file descriptor for a terminal window, which is always fixed, which is 1. And yeah, pointer to our string, which we will see in the moment, and the size, how many bytes you want to write to the terminal. So come back to our code. So yeah, for the shell, our file descriptor is this, a 1, and yeah, R0 is the register for the file descriptor because it's very first one, first function argument, R0, and we push value 1. Now we need to define our string. So that can be done by putting into data section. So you can do like this, data, and then give the label message and simply say what is the data type, this ASCII string, and you can give like hello, yeah, and yeah, you can put new line and other terminating characters as well. So now we need to reference this string. So for that, you just do this likewise, like LDR. Obviously, we want to load the address because end of the day, it's nothing but a pointer. LDR, where we will be loading. Obviously, it's in R1 because yeah, that's where it takes the address. It's a basically second function argument of right syscall. LDR R1 and message label. And then at the last we have how long the string is. So in this case it was 22. Accordingly, like you can see over here, it was like error 404 system not found, but in our case it's like 1 2 3 4 5 6 7 8 9. So let's push 9, move R2. R2 was for the size, and let's push 9. And last is SWI, which stands for software interrupt. So there are two things, SWI, or you can use SVC as well. So SWI was for a bit of the older, SVC is a newer. So SVC for supervisor call. Yeah, so it calls the supervisor and tells you to execute our syscall. This so basically SWI and SWC tells the kernel to execute our syscall. So we will do SWI 0, and we can just exit out. To exit successfully, you need to push 1 to the R7. It's like return 0. So this tells our execution was successful. And again, you have to do SWI 0. Let's compile this and run it. Yep, it has been successfully compiled. Let's see the file type. Yep, it's compiled. And we should see hello world. I guess I did the small mistake. Actually, the new line character also counts. So let's correct that mistake. That's because we take the 9 characters, we should do 10. So it will count the /n as well, but yeah, we are not coming into new line. So let's do make clean. Now you will see other files are gone. Edit your arm tsm.s file and put 10. Now make it again, and you should be fine. Yep, now you are printing to the new line, and we can do s-trace as well if it is installed. I'm not sure. It's installed. Oh, we need to install it, yeah, with sudo. To keep the size small for this virtual machine, many stuff I didn't install by default. Only the stuff which was required for this workshop. You can install anything in this virtual machine basically, like any tools you want, or you can even do the compilation of Radare 2. For a Radare 2, it requires like around 1 or 2 hours of compilation time. Yep, we are done. Like you can do s-trace and execute our file. Yep. So it does this, write one, and one is for output to our, this terminal, and data, and the length, which was 10. So you can see this was one was pushed to R0. This we push the address of the string or a pointer to R1, R0, R1, and then 10 here, the value that was pushed in R2. So yeah, we used R0, R1, and R2. So yeah, is everything clear? Do you have any questions that you want to ask in the chat? Any questions? Okay, no questions. Let's continue. So that was the basic assembly code we just wrote, which was like a hello world. Let's see load and store, and let's debug it inside the GDB. Just remove this file. Let's clean up our files, make clean, gone. Now let's do the load store one. So let's compile it with make. Okay, so maybe we need to do a little bit of organization, I guess. So yeah, for setting a breakpointer is used for during debugging. So you can use this instruction called bkpt, which is to set the breakpoint. Just correcting my file. Okay, should work. So this is example of load and store. So what we are doing is data, and then in data section we define a two variable. One is, you know, the 24, one is 14. So we load R0, address of R0. We load variables one's address into R0 and variable two's address in R1, and then we get the value from the address. So when you, yeah, so what we do is like we push, so R1, so R0, so what contained R0? It contained the address of this where one. What was the where1? Where1 was 24, so R2 has become 24. And what did contain the R1? R1 contained this. Let's examine this in under GDB. Okay, again. I guess I need to manually type it. Haha, can't copy this. It's giving me errors. Let's type it manually instead. It's gonna be tedious, but yeah, we have to do it for sake of the experiment. Oh, there is no file located. Yeah, my bad. Yep. Again, the data section we will define, and then we have variable one dot word. I'm giving any set of values dot word. Let's say 24 dot text. In this we will define a global label start, strt start underscore start. Now we load R0. Oh, you can use the small ones, there is no issue at all. I just like to use caps. It looks more clean to me. And then yeah, don't forget to put the labels for defining our address of where1, which is the reference to where1, adr where2, which is the reference to where2, adr where1. So it will load the address of variable 1 into R0. Let's set BKBT here and examine GDB. Let's just pause the execution over here. Let's make it. Fingers crossed, yes. Open it inside GDB. Now run it. Did it got stuck or something? Info registers. Yep, R0 contains the address, which is this. Let's examine the value. Examine a word from this address, which is 32. So these are the GDB basics. So X stands for examine. The W means word. So yeah, we are reading from this address and the value is obviously 32 because yeah, we are pushing, you know, 32 to R0. Exit out. Yes. Make clean. Again, edit the program. Now this time we will add the address of variable 2 in R1. ADR variable 2, control 4. Make it. Debug it. And run it. Let's run it. And info registers. Now we see the new address get pushed to the R1. Let's the examine value at this address. Examine word at this address should be 24. So now we have successfully pushed, addresses where R1 will have the, there is where the 24 is stored and where the our 36 is stored, 32 is stored. Now complete the rest of the program. So we just go one by one. No problem at all. LDR R2 and this. Oh no. That. Let's do LDR R2. Let's this time do R1 and the value of R0. So from this square brackets, you get a value from a particular address. So let's get a value from R0. So what it will do, it will load a value from the address of a variable 1, which is pretty much nothing but 32. So end of the day, you will have 32 in the, R2, variable 2. Compile it. Open in GDB. run it. Now check the registers values, info registers, and yes, it's a hex 20 which stands for 32. So basically we pushed the value from R0 into R1. So yeah, uh, this was the basic load and store instruction. In the basic load and store instruction, we see how like you can load and store values from addresses to, and you can also do it for between registers. Let's check out for the registers. Oh, let's do make clean and edit the file. Let's load address of 22. Let's do addition and multiplication stuff now instead. So this was basic idea about load and store. Now let's do checkout add. So for add R3, R3 is our destination register, R1 and R2. But yeah, we need value of R, both of the values should be loaded. So we can do with LDR again. Let's decide it like for two. Uh, we will do something like this. R2 will have value from R0. Here R3 will have value from R1. R4 will store the addition R2 from addition of R2 and R3. So your R4 should contain addition of the 32 plus 24, which is like 6 and 556. Make. Let's execute. Let's execute under GDB. Info registers. Oh, run it. Info registers. Yep. You see, R0 had the address of 32, 24, and then we load those particular values with you know R2, R3, and addition was stored in R4, which was 56. Any doubts till so far? You can go ahead and ask me in the chats. If any doubts, please don't be shy. Go ahead and ask me in the chats. I will be reading your comments. No doubts? Okay, let's shall continue. Yep. So now this was the assembly basics you just saw, like what are the use of the R0 to R5 registers. Those are general purpose registers. Those can also hold the function arguments and everything. And yeah, the you can use the syscalls. You can do read and write operations to file and everything. The let's see the interesting shell code, which is very basic one. It's called fork bomb. So fork bomb is nothing but it's a kind of DDoS attack for the CPU. So fork is a syscall again. You can check it out. Man fork. Oops. Yep, it creates a child process. So basically, what I'm gonna do is in the infinite while loop, I am gonna create tons of child process. It will keep on creating a new process in infinite loop. So it will make my OS go really slow. And we will also examine that in the S trace that our syscall is getting executed, and we will extract the shell code as well and test it out. Let's do make clean. So this is the very first basic shell code is ARM fork bomb. Let me find it quickly. Yep, I have put it on exploit DB as well. You can find this shell code or assembly code, not a shell code. No, what happened? I guess, yeah. Yep, this is written by me. So let's copy this. And yeah, put that assembly code inside our file. Oh, let's remove it. I always forget to remove it. So yeah, this is really simple. There is a one extra thing we will doing here, which I will explain you. So yeah, we are creating again in the start. We will put our normal code. So basically, ARM has a feature called thumb mode. The thumb mode was like a ARM version 5. It was supported in ARM version 5 and 6. So thumb mode was your like 64-bit. So it was like used by very low power chips such as STM32 kind of chips, secure chips, and likewise. So this thumb mode is pretty much used in such a really low powered environments. So you can basically switch to this 16-bit thumb mode anytime. What you have to do is add 1 to the program counter and branch exchange to the that address. The program counter, you just do the add the 1 to the program counter and store it to some R3 register and do the branch exchange. And after that, you can just put the core 16-bit code and it will execute. So I am defining one label called loop. EOR is nothing but a XOR. This is for like, this does the XOR operation. So R7 doesn't have any values. They are null, basically 0. So when you do EOR, you are basically like moving 0 to the R7. That's all. That's what you are doing. And then you can do R2. So why I'm showing this, basically like you can push 0 to any register. Like you usually you do this way, like R7 0, oh, this way. Yeah, but in the shell coding practice, it's not recommended to have a null bytes. This will have a null byte in your resulting shell code. So to avoid the direct resulting null byte, what we can do is we can just directly do this EOR R7. So this will basically XOR 0 with 0. Actually, EOR XOR with the register of itself, its result 0. So this will store 0 in R7. So this is just for the example. This line is not necessary. I just showed it for example to create null byte free shell code. This is the one of the techniques. There are many techniques to avoid null byte free shell code. This is Syscall to the fork. Let's check out Syscall to the fork. Yeah, Syscall. Oh, not Syscall, fork. Yep. So for fork, our syscall is 2, as we can see over here. Syscall is 2. Now that's why we are pushing 2 over to R7 and we are executing syscall. So this will create a process, right? This will create a new process. You can set a breakpointer. bk breakpointer. Make okay, you can do the S trace and yep, it executes our syscall and calls the fork. So it will create a new empty process and yeah, it will hit our breakpoint. So let's continue with the rest of the stuff. Again, we move. So we can do also, this is the one more stuff extra I'm showing for shell coding purposes. So you can do move R8 comma R8. So this is your NOP. NOP means no operation. So this will do nothing. Like, let's see, it will do nothing. Let's add bunch of knobs. Yeah. This is for knob. So remember, in ARM thumb mode, when you wanna do no operation, there is like in x86 it's knob directly. It's a knob instruction. In x86 it's knob, but in ARM the entire instruction is move R8 R8. So this is your knob in ARM thumb mode or 16-bit mode. Let's try this out. R8 R8 and set breakpointer. Clean this up. Make it and check it out under S-trace. Yep, it didn't do anything. That's why we didn't see. Let's yeah. Let's now come to the main part, our original shell code. Delete it first. That is make clean. So now this is clear. This is basically pushing 0 to R7. We do the syscall to the fork. We saw that in unistd-common.h file. We do supervisor call to execute our syscall, which is syscall number 2, which is stands for fork. This is one instruction is extra. We are doing nothing over here. And then after we do branch link to the loop. So branch link is like changing the, it changes between it redirects execution to the defined label. So most of the time you can use it for with the if else condition kind of scenario. There are also like branch link equal, or like there are a lot of them. Wait, if I have that document, let me show it to you. No, do I have? Oh yeah, luckily I have that document. Yeah, so this was the PDF I was talking about in the previous slides. So yeah, you have different kind of branching instructions. So you have a branch link, link exchange with link. So each of these are mentioned in this PDF. Let's save this, compile it, and test it out with test trace. You can see it's keep on creating new process. And yep, bye bye to our CPU. You can try to SSH into machine. You can't. Basically, your virtual machine is ran out of resources. You, as long if I quit this, okay, yeah, I cannot quit it. Okay, it's gone. It's completely destroyed. Yep, it says out of memory. It's completely crashed. So we just crashed our system with that shell code. Not a shell code, our assembly code. Just power down or just directly quit it. Bye bye. Starting it again. Game to serial, and we should be normal. Need to check the IP. Yep. It's same. Yeah. Same as before. Yep, we are back. So yeah, it works. Now the question is how we can extract our shell code and put it at the places like exploit DB. So for that I have provided a, for that what you have to do is there is a command for object copy, obj copy, and then hyphen capital O binary, then you pass the our binary name of the binary file, and this will store to like arm asm dot. Oops, arm asm is empty. Or did I forget my command? Is it empty? No, it cannot be. Input. Yeah, it's input. Okay, fine. My bad. In file, out file. Yes, I'll take the same. Why it's this is empty? Okay, that's strange. Let me clean and make it again. I'm hoping that I didn't mess my system. Yep, it's perfectly fine. Then what's the issue? I guess I messed up my system. But I have actually luckily I have Raspberry Pi on my own home network. So I'm gonna switch to it. No. Okay. Let's give us some nice window. This is my own Raspberry Pi, but yeah, you can do the same on your virtual machine. It's no different. Yep. It's my Raspberry Pi. Okay. So let's compile. Nano ARM. Yes. This is our shellcode. Nano Mikfa. Close this. Okay, we can make it now. Ah, there I need to cross compiler. Oh no. But yeah, what I mean is like, mm, I'm not sure what I have messed up with my virtual machine, but yeah. So basically, what you have to do is you run this command object copy, then -o binary, and then you just put this binary file over here. Okay, and then give like this output name of the output file arm.py. Oh, now it's created. Okay, fine. Then run this Python script, which is already given. You can check it in your ASM folder. So yeah, there is a folder. This is the file bin to shell.py. Not here. To shell code.py. Oops. Oops. Make it executable and give the path to the .bin file. Is it? So this was the method. So actually, I don't know why it's not working. Maybe we messed up the system. That's why. But yeah, this is exactly how it will give you the shell code like this. On if you check out on the exploit DB, it's there. Yeah, see, I have put the commands. this you have to do object copy -o, then your actual compiled binary. Let me zoom in if you can properly see. Compiled binary, and then this hexdump command to extract our shellcode. So once this shellcode is extracted, you can test it out with the C program likewise, and this is also given to you in your files, the link which was provided. Yeah, this test shellcode.c is provided, so you can just compile it and test your shellcode. Any doubts for writing a shellcode, assembly basics, how to extract a shellcode from the compiled binary? Nope. So let's continue on. So this is we are reaching at the final stage of our workshop, which is reversing. So reversing binary. So in that one, we will see like we will use the radar 2. So for that reversing, I have put two txt files. So one is example of Fibonacci, which was compiled in .c file, and the assembly was got from the GDB. So let's understand what is happening by line without using any external decompiler or anything. So push R7 LR. So what happens is when the function execution starts, you define a stack frame. After stack frame is defined, you push your return address of a function on the stack, basically. So that is done by pushing value of LR, which is nothing but a return value of a function, to the stack. Now we subtract 24. So as I told you, this subtraction is happening because we are increasing the size of the stack frame. As I told you, stack grows from higher memory to lower memory region. So that's why we subtract 24. We are adding some value. So we are adding 0 to the stack pointer and storing it. So this first three, what is happening over here is basically we are defining our entire stack frame. We first put a return address to the function and then decrement the stack pointer in order to create a particular size of the stack, and then we just push these values to this. We add the current stack pointer and store it to R7. So and yeah, so it moves what it moves, like it moves 0. Okay, it moves 0 to the R3, and it stores something to the R3 from R2 to offset 20. So basically this is some kind of value being pushed to the R3, correct? And then we are adding 1 to the R3. So there is some value being added to R2, R3, and then we are adding it to the R1, right? And then we are saying we are again storing something from R3 to this particular, again then load something and do this. So this entire operation is basically, if you can see over here, R3, this is actually a for loop. If you compare with the core side by side for Fibonacci, you have basically addition happening inside the for loop. So that's what is happening here as well. So this is the entire for like for doing Fibonacci. You can do so. Why I'm showing this, like for any kind of learning reverse engineering, you should compare assembly and the source code side by side. That's how you can develop a basic intuition. Let's try for efiles. efiles.c. This is very simple program you have seen if you have learned C programming. You might already know what I'm doing. Yep, should run. GCC static. We will compile it statically. If else output equals.c. Yep, I expected. Okay, where did I? That's why I don't like that much C program. Oh yeah, we forgot this basically. Else. Yep. Now let's check it inside GDB. First run it to check if it's working. Yep, can't vote because the age is defined is less than 16. 18, sorry. So let's see under GDB how the disassembly looks. GDB, because this list functions. Oh, no simple data. Or you can just directly do, we know the function name since we have the source code. Disassemble main. So yeah, as you can see, the first three, we define our stack frame, then we push 16 to R3, and then we store that in some memory address. So it's R74. So we store it and then again load it for our, you know, if else comparison, and then we compare it with 70 CMP. So we say it like it's if it is less than or less than 18. So compare it with 17. So this is BGT not. So branch greater than, so it's opposite. So this is let's see this entirely in the radar 2. You will get more the visual idea. But you can see what it's doing, like what kind of stuff it's trying to do. Let's see into radar 2. It will give you more idea. Excuse me. I'm trying to copy it out. You can use whatever you like. I'm going to use SFTP, which is for FTP over SSH. Alright, is 5337. User was null. Null. ls. Yep. Get. Exit. See boundaries. So we have our if else binary. We can open it radar 2. So radar 2 R2 AA is for analysis, and we will do if else. You can install radar 2 inside the virtual machine as well. So now while using radar 2, when you want to check out the list of functions, you use command called AFL. So in radar 2, everything is represented, all the commands is represented with a single character. So if you want a help, let's say you want a help for analyze command, so A and then question mark. AF is for analyze functions, and as you can see, L is to list functions. So AFL, and this will print out our entire symbol table. So let's see the sim main. So sim main, and you can print disassembly. For that, the command is P. P is for display sub pd, print disassembly pd, and F to disassemble the current function pdf. Now you can see the stuff more clear over here. and your radar 2 shows you the, you can check out the strings by IZZ. Not that. Yep, IZ, sorry. So IZ prints your strings. What is IZ? Yeah, it searches the various kind of strings inside your binary. So you can do this search string in data section, or you can dump the string from the entire binary, whatever you wish to do. Like, let's see, there will be tons of strings since this is not a strip binary. So strip binary will contain a less and less information. So yeah, you can see these two values. So where this is used, you can find out. AX. So you can, with AX command, you can see the references. We will do references to the address AXT and then this address. So yeah, it's denoted over here, which is like, we actually, what we are trying to see is where this string is being used in which area of assembly. So for that we use this list references. So for that command is AX, and the rest of the you can do AXT at this address. So that's in main. We can do PDF again, and we can see this exact instruction at which it's being done. So it's 10432. It's over here. Yep. So it get address, this address, which is nothing but like, so you can see Radar 2 has also done the pseudocode side in the side. So yeah, you can see compare with 17. If it is, greater than BGT, if it is greater than, then jump over here at this address. So greater than means, yeah, you obviously know you can vote, so it will execute it. Otherwise, if the value is false, it will go over here. So this value, comparison values are actually being fetched from your CSPR register. So yeah, those flag registers will contain values for the comparison. Let me show you the details. Compare. Oh, not compare. CMP. Yeah, you can see it's compare. It updates this values and the flags. Any doubts so far? Okay, okay, fine. So which to the best place where I can learn assembly? So if you want to learn assembly, there are a lot of resources. One I personally recommend is this one, Azaria Labs. That's the best one to learn about ARM assembly. But if you want to learn assembly in the general, there is this book I would recommend. Wait, let me show you the address. Alright, alright. Everything is starting time. This is the book. Nurse, I, yeah, this free book. So you can get this free book, beginners.re. It's a really good book. And for getting pseudocode, you can use various kind of, you know, the I recommend personally. I like Radar too. You can use the Cutter as well. So Cutter is also to get pseudocode. Cutter is a GUI version of Radar 2 you can use. So this is the name of the site. I will show you on the screen. Yep. This one. So this was the website we just saw. And let's check out the cutter. Oops, my screen got locked. Let's check out cutter. Okay, let's go here. Select the file in cutter. Binaries, files. Open it. Yep, you can switch to the main. Decompilers. Okay, I have an issue with decompiler. I don't know. I guess I'm having an issue with, but yeah, you can use Ghidra as well. There are a lot of decompilers you can use. Like this is one the I like Cutter because Cutter is good for like it's a multi architecture support. Sometimes it works, sometimes it doesn't. IDA Pro is all time better. IDA Pro if you have to have support for the IDA Pro as well. So these are the list I will recommend if you wanna use the decompilers or the disassemblers you can say. Radar 2, IDA Pro, Ghidra. Ghidra is very nice. Ghidra you can make tons of plugins as well. To make plugins in Ghidra, you need to know JPython. But to make plugins in Radar 2, any programming language will work. So Radar 2 is more flexible because you can automate entire disassembly decompilation task in Radar 2 because of its thing called Radar 2 API. A lot of automation you can do with Radar 2. That's why I prefer a bit more Radar 2 over Ghidra. Ghidra is like I don't know. It's for Ghidra. It's suitable for a larger projects. You can say, like you have multiple teams working on the reverse engineering project, and you wanna share the project file. So Ghidra has a support for that. You can share. Ghidra is basically made to for a collaborated reverse engineering research. Radar 2, you can do literally anything. the things Ghidra can do, also Radare can do as well. So it depends up to your choice. I hope that answers your question, Shreya. So yeah, we have seen today a lot of concepts within where is I to like we just to be honest, like this was a really like overview of everything. Like what is the low level stuff in the Linux, how the Linux OS itself as a works, what is the binary formats, and like what are the what is the ARM assembly, what is the difference between ARM and the x86 architecture, and likewise, yeah, uh, uh, there are more concepts to this. Like we just saw the like exploit development process, and like we then move to like how you can use this same knowledge, revert the assembly knowledge into the reverse engineering. So like yeah, once you know the instruction sets, you can pretty much start thinking about the source code on your own. But yeah, for my personal advice is that compile various kind of basic C programs in ARM architecture, and have a source code on the side, and see the disassembly output, and compare the source code and the disassembly GDB disassembly output side by side. So today I showed you the basic if else example. You can do anything like for example Fibonacci number or anything, or like any mathematical or logical operation you try to code your own into the C program, and disassemble it in GDB, Radar 2, or whatever disassembler you like, and then try to understand the functionality from its assembly. And if you don't know what that particular instruction is doing, you can set the breakpointer over there and compare it with the source code which you made on the side by side. That's the best way to learn reverse engineering. Yeah, that is my strategy to learn the reverse engineering skill, to compare your disassembly with the source code.